Hello and welcome to this new video where we discuss mathematics and physics on the board. In this video, which is going to at least that I plan to be short, we're going to introduce the Dirac or infamous or famous Dirac delta function. I put quote unquote, and you're going to see why in a minute. So basically that's what we're going to do. I'm just going to give some reasons why it's not a function, like basic ones, and also we're going to look at then how to work with it, and in particular how to derive properties about it. Okay, so basically that's the plan for today. Okay, so the Dirac delta function is denoted by a delta of x, or sometimes delta of x minus x naught, for example. Let's stick with x, just delta of x for now. And the way you may see it defined sometimes would be simply by saying that this is delta of x is equal, so note that I put quote unquote again here, as being plus infinity if x is equal to 0, and then 0 otherwise. Okay, so it's basically, usually it would be represented by a line, sometimes with an arrow on top saying that it shoots off at infinity, and then 0 completely flat aside from that. Okay, now the thing is that when we see a definition like this, does that represent an actual function? Now what we can notice is that if we remove the x equals 0 part and we assume that this thing is defined, let's say, on the reals, then the function would be completely trivial or completely boring if you actually imagine plotting this stuff, because if you again forget about the x equals 0 part, then it's just flat 0 everywhere. It's not even 1 or 2, it's like 0. Okay, so essentially it's basically 0 and that's it. So the whole point, let's say, of no pun intended, of the function is basically what's going on at x equals 0. That's the whole point of that object. But that cannot be a function, because if you remember, when you talk about functions in analysis or in calculus in general, you need to specify what is called the domain of definition. Okay, and the domain of definition is going to be the permissible values of x where the function makes sense. So for example, so if you have a typical function, so actual legitimate ones, let's say you've got f of x is equal to 1 over x. Now, what is called the domain of definition D is going to be, so you can say, well, it's going to be over the entirety of the reals, but then you realize soon enough that if x is equal to 0, this thing actually blows up. And in principle, this is, in mathematics, 1 over 0 is a forbidden move, right? So you don't want to put 1 over 0. So what you do is that you remove 0 from the reals. Okay? So when something strange, like a singularity or something, happens in traditional function analysis or calculus, then we actually remove the problematic points from the domain of definition where the function is supposed to act, and then we can work with this function happily, right? But the problem here is that that's not the case here. As I said earlier, the plus infinity, the blowing up at x equals 0, is essential for that particular object to make sense or exist or have any kind of meaningful stuff to do. Okay, so basically it cannot be a function in the traditional sense of the word. So the thing is that we see that this is quite different. So basically delta here. So so let's say rather that delta of x cannot represent, let's say represent a function. Okay, because it's the almost polar opposite of what you should do if you want to define a function. You don't focus on the points that blow up, you actually remove them and then care about what's outside of these points. Okay, so that's the exact opposite that we want to do here. But the thing is that the actual characterization of the delta function as something that blows up at x equals 0 and then is 0 everywhere else is quite bad, to be honest. So there's a much more, let's say, rigorous way of defining this that is not too complicated, but actually that look at, so let's say, one proper definition. It relies on the following notion. You need to have what is called a set of so-called test functions. So you need to imagine that you've got a test function, and that can be any test function allowed. Usually, I mean, here I'm going to call them phi of x. And phi of x usually needs to have some properties. So if you want these test functions, they need to be, so phi has a finite support. So that's where for support here, meaning the region of its domain of definition where it's non-zero, okay? Or an acceptable choice in some cases is basically that it decays very fast to 0 without having a finite support, okay? So that's one possibility. And then the other part is that it needs to have like phi kind of, people usually can ask for it to be so-called C infinity. So what that means is that it's infinitely differentiable, and and also, I mean, as a consequence of the infinity here, also continuous, like the derivative is continuous as well. Okay. So once you have these test functions, then you can define the delta object, and you say that the Dirac delta, and here I'm going to put x minus x naught, is defined such that for any, so here, by the way, this is for any phi, we have that the integral over the reals of phi of x delta x minus x naught dx is equal to phi of x naught. Okay, that's the actual, or that is an actual definition of the Dirac delta that at least has the advantage of not involving any kind of singular behavior. Okay, so that's how it could be defined. Now, before we move on to showing some properties, what we need to do is realize what does it mean for two objects like that to be equal to each other. So cannot represent a function. And what I'm going to say here is that what is going to represent is when you define stuff that way, then you talk about distributions, not functions. So delta represents a distribution. In the sense of Schwartz, and one of the things that what that means is that if you've got so if f and g are two distributions, so two dist here for distributions, then f is equal to g. But again, in the sense of distribution, sometimes people are going to call that a weak equality. And sometimes all of these things happen in the context of differential equations, where people talk about weak solutions to differential equations. Here I'm going to call that an equality in the sense of distributions. And so what we say is that f is equal to g if you have that for any phi. So again, any test function that has these two properties, any of them, if you have actually takes the integral over r f of x phi of x dx is equal to g of x phi of x dx. Okay, so that's how we define the equality of f and g. Okay, and so here there are two properties I would like to have a go at, really, and that's the following. So I'm going to, yes, that should do. So that's again equality in the sense of distributions. If for any test function f of x, integral of f of x phi of x is equal to integral of g of x and then pi of x. Okay? Okay, so the first property we want to show is the following, that delta of minus x is equal to delta of x. Okay? So where we start from is basically we apply again the integral of any test function over R, so phi of x, then delta of minus x dx. Now, I don't know actually what this object does, okay? But what I know is that I can substitute x to, let's say, x is equal to minus u, okay? And so that's going to give me dx is equal to minus du. And then I need to be a bit careful with what I'm doing here, because the integral I is going to be the integral from minus infinity, so from plus infinity, sorry, to minus infinity. Then I've got a minus sign. Then I've got phi of minus x, minus u, sorry, and then I've got delta of u, du. Okay, and basically the plus infinity minus is going to give a plus, and the delta u is going to return phi of 0. Okay, but basically phi of 0, I know that this is equal to the integral over the reals of phi of x delta of x dx, and this is true for any test function phi, and therefore we've got that delta of minus x is equal to delta of x. Now, the follow-up of this is that if you've got delta of x minus x naught, then essentially here you're going to have delta of x naught minus x is equal to delta of x minus x naught. Okay, so we need to be a bit careful with this. Okay, so the second property we are going to show is this one, that the integral over R of delta of x, in fact that can be over x minus x naught, this does not necessarily matter, x minus x naught dx is equal to 1. Okay, so how does that work? Well, I'm going to say, well, let's imagine that f of x prime, in fact f of x, let's say that f of x is a distribution that I don't know, that is the integral of delta x prime minus x dx prime. Okay, so I'm just saying I don't know what this stuff is. Okay, now what I'm going to do is trying to see what happens when I put a test function and then against this particular f here. So if I have I is equal to the integral of some test function phi of x f of x over the reals, then this is going to be equal to the double integral over the reals of phi of x, and then I've got delta x prime minus x dx prime. So the only thing I want to show here is basically that I simply need to say that this is equal to delta of x minus x prime because of the property we've shown earlier. And so then I need to integrate phi of x delta x minus x prime. And so that's going to give me the integral over R, and then phi of x prime dx prime. And so you see that basically here I've got an integral of phi of x with f that is equal to the integral of phi of x prime with 1. And that completes kind of the proof. So that basically the integral of delta x minus x naught is equal to 1. Okay, so these are two important properties of the delta function. Of course, another way to show that is simply saying that the test function being used is actually 1, and so you just return 1. But the problem is that the function 1, that would be 1 everywhere on the reals, is not defined on a kind of on a support, on a finite support, right? So on a compact support. So that's why it's not that trivial it's easy to remember, but it's not that trivial to actually prove it. You need to play a bit with these ideas here. And basically, that's it. So that's how you actually show these two properties. From these two, there are some others that you can prove as well that are very useful. If you want, we can have a go at them in some other video. So that's it. So if you've got any questions or comments, do let me know in the comment section.